Hello everyone. So we're going to be splitting section 7.1 to 7.4 over 3 videos, which will each be 15 minutes each. I thought this would be much better to review for finals so that we don't have to rush when you get back, and also so you can use these to look back on if you would like to. So first, before we get into anything new, the first video is going to be a little bit of review and then a discovery of the new formulas. So first, something we did talk about briefly in the past when we did chapter 3 was something called the midline theorem, where if you happen to have a triangle where the segment hits directly in the midpoints, so these two segments would be equal there, and if these two lines are parallel, the midline and the base, then you have a situation where this length is exactly half the length of this third side. And that is called the midline theorem. Something else, though, before we find those two blue lengths that's interesting, that has to do with your previous chapter 5 material, is if these two lines are parallel, these two angles are corresponding, so they must be congruent. So if you were asked to find the measure of angle ABE, you would know that this red angle would have to be 70 degrees, because if parallel lines, then corresponding angles are congruent. Review. Love how it keeps coming back. If you wanted to find the measure of angle A, you know that this is 70 degrees. If this is 70 degrees, you know that y plus 15 equals 70. So y equals 55, which means that this angle itself is actually 45 degrees. So if you wanted to find the measure of angle A, if you add up 70 and 45, you get 115. So if you take the triangle total measurement minus 115, I believe you would get this angle here is 65 degrees. So the measure of angle A is 65. The other part of this theorem that was mentioned earlier is if it was given to you, sorry about that, if it was given to you that the measure of BE is 15, the measure of CD, this is D here, is 15 units, what is the measure of BE? Well, because the midline happens to hit the two midpoints and is parallel, it ends up being exactly half of 15, or 7.5 units. And yes, this does work the other way as well. If you were given BE was something like 4 units, CD would be double, or 8 units. So keep those theorems in mind, just for final exam review mainly. Other things to keep in mind, recall, are the exterior angle theorem and just the triangle sum theorem. Some of you might recognize this picture from your Chapter 3 quiz, your Chapter 3 test, and also multiple homework assignments. This triangle, when you look at it, please do not assume that it is isosceles, because these two whole angles are not equal. But we do know, because the triangle sum theorem, that this little triangle down here, we could say is x plus y plus z equals 180 degrees. And because we have the larger triangle as well, this whole angle is 2x, this whole angle is 2y. So another equation could be 2x plus 2y plus 80 equals 180. And if we simplify this green equation a little bit and divide everything by 2, we can get x plus y plus 40 equals 90, or x plus y itself equals 50. The reason this is quite handy-dandy is because you could use the substitution theorem, that you know x plus y is 50, so in the original blue equation, x plus y can now be replaced with 50 completely, but you still have plus z equals 180 degrees. So using this method, you would get that z is 130 degrees. So please make sure not to assume that this triangle is isosceles. Last review topic is the exterior angle theorem, which said in the past that if you have any triangle with an exterior angle, the measure of the exterior angle is the two non-adjacent angles added up. So in this picture, the exterior angle x would be equal to y plus z. And so these two examples here, one of them you need the exterior angle theorem more than the other. The second one you're going to need it more, but let me show you on problem 1. You could say that the exterior angle 130 equals x plus 60, and if you did that, you would get x equals 70 degrees, which is correct. If you didn't see the exterior angle theorem though, you could say that this angle is the supplement, so it's 50. Then 50 plus 60 gets you 110. Subtract from 180, you still get 70 degrees that way as well. Unfortunately, in the second problem, we know that y plus 2x plus 4 equals 180, but instead of setting up a system initially, we could say that the exterior angle of 2x plus 4 is equal to the sum of the two non-adjacent angles, x plus 30. And if you do this, you actually avoid a system of equations because everything's in terms of the same variable. So if we solved this by subtracting x and then subtracting 4, we'd get x equals 26. So we found x. So x is 26 down here. I'll circle that. If we wanted to find y, probably you could do one of the two things. You could either plug in x here as 26 degrees and use the triangle sum theorem. You could also plug in x here and find the supplement. So let's see, if I did the supplement, 26 times 2 would get me 52 plus 4. So this angle would be 56. And the supplement of 56 would be, let's see, 4, 7, I think 124 degrees. And if you did that as well with the triangle sum theorem, you would get 124 as well. Now is time for some of the cool new things. For instance, some vocabulary for you. A lot of this you've probably heard of before. Names of polygons. If a polygon has 3 sides, it's called a triangle. If it's 4 sides, as I'm sure you well know, it's called a quadrilateral. 5 sides is a pentagon. 6 sides is a hexagon. 7 sides is a fun one, heptagon. 8 is an octagon. 9 is a nonagon. 10 is a decagon. And 12 is also pretty popular, a dodecagon, pretty fun to say. Another popular one that comes up is 15 sides, which is a pentadecagon, also pretty fun to say. But anything beyond that, mathematicians got kind of lazy, and they didn't want to make up any more neat names. So for instance, if a polygon happens to have like 117 sides, we just call that 117gon, which sounds so ridiculous, but makes life easier, kind of like how we name it slope-intercept form, because it has a slope and an intercept. We call it a 17gon because it has 17 sides, and it's easier than making up a new name. So keep this big list in mind. It'll help as we keep going. So time for some discovery. We have these formulas that come up in section 7.3 that have to do with finding all these interesting things about a polygon. But instead of just giving you the formulas straight out, I want to show you where they come from. And if we don't finish everything in this video, we'll continue on in the second one. So let's say that we're talking about specific polygons with a certain number of sides. 3 sides would be some kind of triangle. 4 sides would be some kind of quadrilateral. I'll draw something with 4 sides, not necessarily a square. 5 sides, 1, 2, 3, 4, 5. And 6 sides, 1, 2, 3, 4, 5, 6. So in order to figure out the total number of interior angles, or to find the sum of the interior angles, let's go through a couple things first. If we look at the blue shapes that I drew down here, I want to know how many triangles can be drawn within each of these shapes, starting from only one vertex. Here's what I mean. If I put my pen on a vertex, am I able to draw any diagonals in this triangle? And the definition of a diagonal has to be from a vertex to another vertex. So if I tried to draw a vertex, that already exists and this already exists. So really, how many triangles can be drawn? Well, no more, but we do have one initially. So only one triangle in a 3-sided figure. In a 4-sided figure, or a quadrilateral, if we have our pen on one vertex, how many diagonals are we able to draw from this particular vertex? Well, we can definitely draw this one from vertex to vertex, but these two are already drawn. So how many triangles now exist because I drew this diagonal? 1, 2. So now there are 2 triangles that exist in the interior of the shape. In a 5-sided figure, if I put my pen here, how many diagonals am I able to draw from this particular dot? Well, here's a new diagonal, and here's a new one, but these two are already drawn. So how many triangles did I create? Well, I created 3 within the interior of my 5-sided figure. And then if I keep going to the 6-sided figure, here's the vertex I chose. I'm able to draw 1, 2, 3 diagonals. These diagonals are already drawn, so I created 1, 2, 3, 4 triangles within my 6-sided figure. And so what's interesting is we could do this forever and ever, and I want to use this information to figure out how many total degrees are in each figure. Well, we know from the past that every triangle has 180 degrees. So that means that this figure, without much work, has 180 total interior degrees. The second figure, because I have 2 triangles, each of these triangles have to be 180 degrees, so we have 360 total degrees. And the idea continues. If I have 3 triangles, each 180 degrees, 180 times 3 gets me 540 total degrees. And in a 6-sided figure, 4 triangles, 180 times 4, or 180 degrees added 4 times, gets me 720 total degrees. And again, as I said, this pattern is going to keep happening. But imagine if I asked you to do a 100-sided figure. First, you'd have to draw a 100-sided figure. Then you have to draw the number of diagonals that are possible, figure out how many triangles that is, and then multiply by the number of triangles you have. Talk about tedious. So I wonder if there's a way that we could reduce the work and find a particular pattern or an equation that comes from this information. So let's take a look. The number of sides in general in this section is labeled with the letter N. So if I start with 3 sides, notice that from 3 sides we go down to 1 triangle. From 4 sides we go down to 2 triangles. From 5 sides we go down to 3 triangles, and from 6 sides we go down to 4 triangles. So if I was going to represent that in terms of a pattern here, my number of sides is n, and each time it looks like I'm subtracting 2. So what if I said the number of sides minus 2? Now, what did I do to get from the number of triangles to the total degrees? Well, we said that each triangle is 180 degrees. So would it make sense to say that if we multiplied the sides minus 2, would we end up with all of these answers? Well, I think it would, because the sides minus 2 gets me the total number of triangles that I have, and we multiplied each number of triangles times 180. So let me show you with one of these examples that it would work. Let me pick the 6-sided figure. If I said that I have a 6-sided figure, or n is 6, if I plug in 6 minus 2 times 180, I would get 4 times 180 degrees, which would be 700 total degrees without drawing the picture at all. And so good news. If I wanted to find the sum of the interior angles of a polygon, the little quick formula would be the sides minus 2 times 180. So that ridiculous example I made up before, what if you wanted to find a 100-sided figure, how many degrees are in there? Now, we could take 100 minus 2 times 180, or 98 times 180, and get the answer much more quickly than we did before. Okay, so we do have a couple more discoveries. However, we do not have time within this first video. So if you're willing to go to the next video, which is going to be a couple more discoveries and then going to some example problems using them, I would very, very much appreciate that. And thanks for tuning in, guys. I'll see you in just a minute.